So continuing in our topic of similarity, we're going to take a look at angle bisector theorem and then some other properties that are going to come up along the way with our triangles. So first thing we're looking at is this angle bisector theorem. And it's telling us that first off we have to make sure we have an angle bisector. So the angle bisector of an angle meets the side across from it. It gives us this ratio. It says then our segments, I can use this ratio. It says BD compared to CD is going to be the same thing as BA compared to CA. So if we were to take a look at this triangle below and maybe just label it so that we can compare that theorem with a visual. So we're saying the angle bisector at A meets the side opposite at point D. It's saying then we get this ratio. The ratio of BD compared to CD is going to be the same thing as if I compared BA. Notice how I'm staying on that same side. We started on the left side, went to the right side. Now I'm comparing BA, left side to right side. And just to kind of give you an idea, if we were to look at this program that we have on our calculator, I could try and show you that same idea. So if I take that expression and I'm going to try that idea, I'm going to divide the left side by the right side. So we can see that dividing AX by CX, we get 104. And if I were to do the same thing with AB and CB, so clicking, I would click AB and then I would divide it by CB. Notice I'm going to get the same value. And if I were to move the triangle, and watching those values, I can see that even if the triangle was a different size, I would still get those two values. Now, we will also see that this extends to a different set of calculations, where if I took the left and divided it by the left, or if I took the right and divided it by the right, again, I would get the same values. So this angle bisector theorem gives us really two different proportions that we can set up, as long as we are consistent in the way that we are comparing. So we're going to try this on number one. It says the sides of the triangle have lengths 12, 16, and 21. The length of 21 is our side BC. So this whole thing is 21. It says an angle bisector meets the side of the length 21. We have to find lengths X and Y. So first thing, if I were to set up a proportion like we had talked about, an issue I'd run into is the fact that I would have two variables. And if I have two variables, I need two equations. So rather than doing that, if I know the entire segment of BC is 21, that means I could represent this section of Y as saying, well, really it's going to be 21 minus whatever X is. Okay, so that gives us the chance now to set up our proportion. And up above, using the one that we had, it said I would compare that side that the angle bisector meets. It said we would compare BD to CD. Okay, so BD is 21 minus X over CD, which is X. Should be the same thing is if I compare, now so we went left to right, I'm going to do the same thing, left, which is 16, to right, which is 12. Okay, and now we're going to cross multiply this to solve. So I have 16x is equal to 12 times 21 minus x. Keep in mind to simplify, we need to distribute. So 12 times 21, I'm going to have 252 minus 12x. We want to get the x's together. So we're going to have 28x equals 252. And if I divide through, I can find x is going to be 9. So now keep in mind, we wanted to find the lengths of x and y. we had already stated in the beginning y was going to be equal to 21 minus x. So if I do 21 minus 9, that means y is going to be a total of 12. So now we have our measurements. Keep in mind, like we had shown on the calculator, you could also set up other proportions as long as you are consistent. So we said the other set of proportions that also worked was we have already compared the side that the angle bisector hits, comparing left to right, and then the triangles left to right. Your other option is comparing left side to left part and right side to right part. So setting something up like this would be okay as well. And if you notice, the reason why, if we do that cross multiplying again, notice what you get. 16x is equal to 12 times 21 minus x. Same thing that we had over here. So that's why we can use that ratio, and we can solve that two different ways, setting that up two different ways. Okay, number 2, similar idea. The perimeter of this triangle is 22 and a half. So thinking perimeter meaning all of our sides added up. So WZ bisects that angle. So now I have an angle bisector hitting a side of my triangle, gives me 2 parts, meaning I know I can compare these 2 sides along with these 2 sides. And it says we have to find these. Okay, so I have to think up above. If I could compare these 2 sides here, and I could say UZ compared to VZ should be in the same proportion as UW as compared to VW. Okay, well, if I think it's in that same proportion, the proportion I have here is 2 compared to 2.5. So this should also be 2 of something compared to 2.5 of something. They should be in that same ratio. Well, what that does is that gives me a value for all of my sides of my triangle, and if I know I have a perimeter, that gives me an equation I could set up. So if we were to add them, 2x plus 2.5x plus 2.5 plus 2, added all up, should equal 22 and a half. Okay, so if we solve, so I have 4.5x plus 4.5 is equal to 22.5. And subtract over my 4.5, that's going to leave me with 18. And if I divide through by 4.5, now I'm going to have a total of 4. So what is that showing me? Well, if I go back, that's showing me if I were to plug that in, this side would have a length of 8. And 2.5 times 4 would give me a length of 10. So if I wanted to check and just make sure, does that angle bisector theorem work, we'll set up that proportion. So we said 2 over 2.5, is that the same thing as 8 over 10? And if we cross multiply, 2 times 10 I get 20, and 8 times 2.5 I also get 20. So we've checked our work, we know that it works, and we've used our angle bisector theorem. Okay, so moving on, some other important properties that we get, again, going with that similar triangle idea, is looking at the ratio of sides and perimeters and areas. So if I were to do the ratio of the sides of these 2 triangles, if I compare 36 to 24, I could do the same thing, like say with the hypotenuse, 39 compared to 26, or I could do the short leg, I could do 15 to 10. And if I looked at all of those are going to simplify down to a ratio of, let's say, 1.5 to 1. Okay, so what about the ratio of the perimeters? So the perimeter here, we're adding up all of the sides, right? So we got 36 plus 39 plus 15. That's a total of 90 units. And if I do the same thing over here for a perimeter, adding up all of the sides, 24 and 26 and 10, I get a total of 60 units. So if I were to make that ratio, now keep in mind we went big to small for all of these, big triangle compared to small triangle. Same idea here, I'm just going to keep that same order, big to small. Our ratio would be 90 over 60, which is again going to get us that idea of 1.5 to 1. If we wanted to look at this different, if decimals are kind of like this is weird, if I could simplify, let's even say this fraction back here. If I simplified that, I know 5 divides in evenly to each of those. That would give me something that looks like 3 over 2. Same thing here. If I were to reduce this, that would give me something that looks like 3 over 2. So you have options. You could do the calculator and get decimals. You could reduce fractions and see what your fractions look like. Okay. And the ratio, or yes, we're going to compare the ratio of the areas. So we have to find the area. Area, keep in mind, for a triangle is 1/2 base times height, where your base and your height are measured with perpendicular lines. So our perpendicular lines are our 15 and our 36. So that gives us an area of this one of 270 units squared, label for area. Over here, same idea, we have 1/2 base times height. Base and height are 10 and 24, measured with our perpendicular line, and that's going to give us 120 units squared. So if we compare those ratios, again, we're going to do our big to small. I can see here we have a ratio of 270 over 120. Now, here's where the decimals may be a little bit tough to see. If you were to reduce this out on your calculator, the decimal form that you get is 2.25 over 1. May not be as easy to see the connection that we have with our ratio of our area and our perimeters. If we were to reduce 270 over 120 as a fraction, I could see this would get me the fraction 9 over 4. That might make it a little bit easier to see this connection. If I wanted to connect these two, well, if I took 3 and I squared it, and I took 2 and I squared it, that's going to get me the same ratio. Okay, so that brings us to an important fact that we have below. It says, so if I'm looking at, first off, the ratio of perimeters, but this also connects to the ratio of altitudes, medians, diagonals, angle bisectors, any of those important segments. If we know our polygons are similar, their corresponding sides and altitudes and medians and perimeters are all in that same ratio. We saw that back up above. We have the sides being in a ratio of 3 over 2, and perimeters being in a ratio of 3 over 2. So it says if the sides of two similar triangles are in the ratio of 4 to 9, what's the ratio of the perimeters? Well, it's the same, 4 to 9. And we could extend that out and we could say what's the ratio of their altitudes? 4 over 9. Or the ratio of the angle bisectors? 4 over 9. They're always going to be equal. Now, if we look at the ratio of the areas, it says the ratio of the areas is equal to the square of the ratio of their corresponding sides. So let's go back up here. And remember how we compared the ratio of the perimeters. Even if I look at the ratio of the sides, keep in mind, ratio of the sides, if I squared 3, I got the ratio of the areas. If I squared 2, we got the ratio of the areas. Okay, so back down here, it says if the sides of two similar triangles are in the ratio of 3 to 5, those are the sides, I want to find the areas. So if this is our side ratio, we said square the sides, and that would get us the area ratio, which would be 9 over 25. I don't know what the areas are, but I know that their area is in that ratio of 9 to 25. Now, if we extend this concept, thinking, well, what happens with volumes? Well, volume is going to be cubed. And if you notice, the ratios are all connected to how we would label these things. So in area, we would always have units squared. The ratios are squared. In perimeter, we just have plain old units. So they were the same as the sides, units. If I'm going to volume, now our volume label is cubed, so our ratios are cubed. Okay, so for instance, if the sides of two triangles are in the ratio of 2 to 3, so now again, these are our side ratios. Okay, trying to find the volume ratios, well, if I'm thinking, what would I do with the units? I'd have to cube the units. that would tell me that then our volume ratio should be in a ratio of 8 to 27. Okay, again, I don't know what the volumes are, but I can tell you that the ratio of the volumes would be 8 to 27. We'll do more of this in class. Hope this helped. And don't forget, like and subscribe. Have a great day.